Our goal is to generate continuous trajectories. But how do you do that? Let's start with a naive approach and then get more realistic. Let's say our car has been driving along the road at a constant speed for some time. The s versus time graph is just a straight line, since the velocity is constant. And the d versus time graph is flat, since the car is just staying in the center of the lane. Also note that I've shifted my axis a bit so that the origin of the frame is our current position in s, d, and t. This will end up being computationally efficient later. Now, let's say we're getting off this highway soon. So we want to change lane in order to end up there, after some delta t, which let's say it's 10 seconds. On the s and t graph, that goal would be here, and here. The start position and goal position are fixed. They define what we call the boundary conditions of our trajectory at t equals 0 and t equals 10. If those were our only boundary conditions, then we might consider s and d trajectories looking like this. But it turns out that these aren't physically possible. This kink in the slope would translate in an instantaneous jump in speed, which would require infinite acceleration. Now, if we were to send that to our motion control module, maybe they can track this trajectory, but probably not. And even if they tried to track it, it would result in a very strong acceleration of our car, which is both uncomfortable and dangerous. This is why we need both continuity and smoothness in our trajectories. But how much continuity and smoothness? We know we want continuity in position since our car cannot teleport, and it would not make sense to compute a trajectory starting 10 meters ahead of us. And we also know that our car cannot instantaneously change speed, therefore the speed should also be continuous. Following this logic, you could also say that the acceleration should be continuous, and maybe the acceleration's derivative as well, and so on. Position becomes velocity, velocity becomes acceleration, acceleration becomes jerk, and going even further, you get snap, crackle, and pop. It turns out that one of these quantities is directly related to human perception of comfort. So let's think about it. In a vehicle, humans feel discomfort when which of these values is high? Velocity? No. When they cruise down the highway at high velocity, people usually don't find it less comfortable than when they drive at lower speed. And if you think about airplanes, they move very fast, and they aren't really uncomfortable. Acceleration maybe? That's slightly more tricky. We are indeed sensitive to acceleration, but mostly when it becomes very high. For example, we're all used to supporting acceleration up to 1g, which is the most you can usually sustain in a normal car. Therefore, we shouldn't reach acceleration levels that are high enough to become uncomfortable. Jerk then. It turns out this is the quantity that humans perceive as uncomfortable. We can tolerate high acceleration, but we don't like it when our acceleration changes too quickly, which is high jerk. So when we design trajectories for self-driving car, we would like it if they were jerk minimizing.